Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today on the bench is a power supply that has failed. Let's do some diagnosis, and let's fix this power supply. Let's make it work again, just like everything that hits the bench at Mr. Carlson's Lab. Let's get started. This is the power supply that we together are going to diagnose and repair. Now, I've owned this power supply for many years, and I haven't had a single problem with it. The thing has worked flawless. So aside from me sliding the insides out of the case to mount this below those two very large oscilloscopes, I haven't been beyond that. And when I say I haven't been beyond that, inside this thing is a large black heatsink with a bunch of pass transistors. So I've never removed that and actually been into the power supply. So we'll discover what's underneath that black heatsink together. So I'm kind of excited to see how this thing actually is put together. Now, it's been a really great power supply, and I use this all the time. Now, since this is normally below those two oscilloscopes, I've mounted this above my microscope there, and whenever I'm working on a project under the microscope that needs to get powered up, I use this. And since I'm designing a new piece of test equipment on Patreon that I'm going to be releasing here quite shortly, I'm working under that microscope a lot lately, and I turned the switch on and absolutely nothing happened. And I'm very surprised because when I shut the thing off the last time, everything was just fine. So I really don't know what happened between then and the next time I turned the thing on. Very odd. So I'll give you an example of what's going on here. So it's not plugged in right now. I'll just plug this into my isolation transformer and current limited variac supply. I'll turn that on, turn the switch on, and as you can see, the light comes on, but nothing happens. So this usually indicates that the primary of the transformers is, getting AC. Now, if I move the voltage adjustments around, this would normally move, right? There's nothing there. And on this side, same thing. Now, this is another thing that really bothers me that I'd like to address in this power supply, and it's bothered me since I've owned this thing right from the beginning. So to give you an example, all right, so turn this down. As you can see, it's ridiculous. Okay, so now say I'm at 0 volts and I need to get to 25 volts. Really? That's 25 volts now. So I can do that with a single turn potentiometer. So I can get, a couple zeros out of it. So if I want 5.00 volts, I can do that with a single turn very easily. I don't need to have 10 turns to do that. I guess if you're fumbling around and you want to quickly get to, 2 zeros or whatever by doing that, I can sit there and just do that, and then I'm at 2 zeros. It's just that easy. So I want to get rid of those things. It drives me crazy, these two things. The current won't display anything unless there's current being drawn, and this is the current limit, so this sets the current limit. So that is a single turn. That's nice. So what's very interesting about this power supply, and this is part of the diagnosis procedure already. Now, again, I haven't been below that heatsink or anything. I haven't done anything at this point. You know as much as I do. We'll discover this all together, and that's kind of the fun of this whole thing. So now when the power is on, I can hear the power transformers turn on. Now, this is a linear power supply. This is not a switching type power supply. It's really heavy. It's got two big transformers in the back, and I don't think you can hear this, but I'll try anyways. When I click the switch on, you'll hear the transformers hum for a moment and then settle off. So they go, when I first turn the thing on. All right, so let's see if you can hear it. All right, I'll do it one more time. Let it sit for a second. All right, and I'll turn it on again. So when I first turn it on, it goes, So that indicates to me that there is obviously current getting to the primary of the transformers inside this thing, but nothing is happening here. Now, the reason that when you first turn this thing on, well, it could be a couple of things. You're not turning the thing on in zero cross, or it could be charging a bunch of filter capacitors inside this thing, and that is most likely what's happening because every time I click this, it does that. So, yeah, there it is again. That was very pronounced right there. So that was probably empty filter capacitors and turning this thing on at the peak of the AC cycle. At any rate, that tells me that the primary of both of the transformers in this thing are receiving AC, and there's a really good chance that those transformers are charging some filter capacitors, 1, 2, however many is in this thing. It'll be charging them up, right? So that already tells me I've already diagnosed a bunch of this thing without even having to remove this thing from the case. That's just from listening and, looking at the signs. Now, if I was to click this on and this lamp didn't come on, of course, immediately I would suspect a fuse or something like that. But the fact that I can turn the thing on and nothing happens on either side is very interesting. Maybe both sides are controlled by one particular area in this thing. As I say, I don't know. We'll open this thing up and find out what's going on here in just a moment. So at any rate, I need this thing to work, and I need to use this because I'm designing that new piece of test equipment, and I was relying on this thing and it just stopped. So let's make this thing work. So one of the nice things about this power supply and the engineers that put this thing together, and I do give them a hand, is it's extremely difficult to get into the case of this thing. I'm being silly. There's one screw. That's it. You remove one screw and the whole thing comes apart. Slide the whole thing out. That's good design. The case is nice and tight. It's held together very well. And all you need to do is remove one single screw and the whole thing comes apart. That's great. Now, beyond that inside, there's obviously going to be more screws holding that heatsink on and everything like that. But we'll address that when we get inside this thing. So what I'll do is I'll reposition the camera above this thing. I'll slide this thing out of the case. Let's take this thing apart and start fixing this thing. Let's make it work again. Because I really like this power supply. It's a great power supply. Look at it. It looks nice with those meters in the front and everything. Isn't that a nice looking supply? All right, let's make it work. All right, let's open this thing up and see what's inside. Okay, so nice soft mat here. Tip this up like so. And hopefully there's enough room between this and the camera. I'll move that up. Get that out of the way. Of course, the unit is unplugged while I'm doing this. Alright, just move this around. Get this line cord out of here. Line cord comfortably slips through that little hole there. Okay, so there's the top side. The usual dust and stuff on here. All right, so looks like this is a smaller Phillips. These ones here I'll remove. Kind of the plastic is yellowing. Definitely an older supply. Been very good to me. Grab this. Is this one the right one? It is. Now, one word of caution. Of course, you want to make sure that this is unplugged from the wall. And as you can see, I'm putting this in here. I don't want to accidentally touch this to a pass element, because usually the cases of these things, the collector of this, it says on there 2N3055, which is probably one of the most common transistors on the planet. At any rate, I wouldn't want to touch this, come close to that and touch that, because if there is a large filter can charged up inside this thing, really bad things could happen. I'll just create a lot more work for myself if I do that, so I'll just keep that away from there. And go over to this side over here. So you got to remember, in these linear power supplies, there's usually large capacitors inside that do the filtering. Now, 2 amps isn't a whole lot of current. It's not going to be crazy big, but still big enough. Looks like you're going to have to move this off to the front. So I'll just move this over like this. Looks like this is going to come very close to those meters. I don't want to scrape those meters. It sits right below it. Okay, good. That's what's inside this. Wow. That's actually really nicely put together. Kind of a nice surprise. Usually this older stuff is very well designed. And this is no exception. These nice big transformers in here. And the filter caps. So, a very quick shortcut here. Usually when they socket things, those are the suspect issues. Okay, so the reason that they socket those things is for a reason. And of course, the pass elements on the top are socketed as well. Now, whenever any type of linear power supply, is bad, the first thing is obviously check the fuse, and then of course, pass elements are the suspects. Now, unfortunately, usually when a pass element fails, there's a reason that these are socketed as well, because they usually take out the little IC. Now, this is an IC that I have not seen in a very long time. This is an MC, so Motorola, 1466L. So MC 1466L. Date code on the bottom, 77. And this one here says 74. So very old ceramic type ICs, and these things are no longer available. And they are not a very common part. In fact, they're getting very difficult to find. So I haven't seen an MC1466L in a long time. And the fact that it's ceramic too, very nice. They're very nice ICs. So hopefully those aren't bad. Hopefully both sides aren't working. And as I say, I just turned the switch on and nothing happened. And I'm telling you, I turned the switch off the last time, turned it on the next, and there's just nothing there, which is odd because there's two power supplies and both sides aren't working, which is really odd to me. So I don't know. I'm thinking maybe a really bad static discharge or something maybe in here. I have really no idea at this point. At any rate, so the first thing that I want to do is I want to make sure that the capacitors are discharged. And how I'm going to do that is I'm going to turn this thing on its side, or maybe even upside down. And as you can see on the bottom, there's a bunch of screws, and those two screws are going to be what I want to test. So what I'm going to do is I'm going to go get a meter. I'll get a meter in the shot here, and we'll make sure that those caps are discharged properly. I'll be right back. I have my capacitor discharge device here, and what this will do is this will indicate to me when the capacitor is discharged. So this box will safely discharge those capacitors, and I'll be able to see when the charge on the capacitor is, basically gone. Now, I've added provisions to add an external meter as well. So if I actually want to watch that fall on an external meter, I can do that. But I'm just going to rely on these LEDs right now to see if these are actually charged up. So here we go. And there's nothing there. No, everything looks like it's safely discharged. And here's that other capacitor. Nope. So there is no charge on those capacitors at all, so I'm okay. So this is another thing that I've released on Patreon if you're interested in the capacitor discharge device. So I use that all the time for working on vacuum tube equipment and this stuff as well. And it allows me to safely discharge these without any big sparks and without hurting anything. Okay, so what that tells me now is that I want to be testing these pass elements. So both sides are toast. So, like when I say toast, I mean not working. So both sides, let's put this like so, or like this, and there is no charge. So what's nice about these is I can just very quickly remove a pass element and test it. So what I'll do is I'll grab a screwdriver here, and I'll just remove one side. Now both sides aren't working, so if I remove one side, and these are okay, then that's in there pretty tight. There we go. It could have been a little bit more thorough with that compound. Just move that over here. Not very much heatsink compound on the bottom of these things. So at any rate, I'm going to go get a tester here, and I will just beep this out with a normal tester. So give me 1 second here, and I'll be right back. I'll go grab a tester. This is the NPN pass element off the top side of the heatsink there. So this is a 2N3055 NPN transistor. So in order to identify the leads, it's very easy. So if you can remember, the leads that are closer to the far end, so if you have the transistor sitting on the bench in front of you and these leads are closer to this end, so they've set the leads off closer to one end so that this is indexed, so it'll only go in one way, right? So if you can remember, when the leads are closer to the far end, this is the base, emitter, and collector. So this lead is the base, this lead is the emitter, this is the collector, and this is an NPN transistor. Now you can also memorize it the opposite way around. Some transistors actually have it written this way, and others, don't have any writing on them like these ones here, right? So we can test this very simply with just a simple little tester that I've built, and I'll also show you how to test this with a standard DMM here in just a moment. So if this tests okay, this will be blue, red, and blue. So blue being N and red being P, okay? So N, P, N. So blue, red, blue. If it was P and P, it'd be the other way around. Red, blue, red. So let's just connect this up here, and I'll show you how to test this with just a standard DMM in just a moment. Okay, so we'll go emitter. And I'll go collector. And base. So if I get two colors glowing at the same time, like a purplish looking color, there's a short. If it's just red, blue, and red, or blue, red, and blue, it's okay, right? Depending on whether it's an NPN or PNP transistor. And there we have it. NPN. And it's okay. So again, if this was shorted, so if you saw something like this, it kind of blows out on the camera a little bit. Here, I'll just hold that against here and put my hand over it so you can see. See how it's kind of a purplish, kind of pinkish kind of color? That's because both the blue and the red are glowing at the same time. That means that it's shorted. Okay, so this transistor is fine. Again, as you can see, blue, red, and blue, right? NPN, no problems. Nice thing about this is this will also detect leakage in transistors very easily as well, and I can display that with the other transistor here in just a moment. So I'll get this out of the way and I'll show you how to test this with just a standard DMM as well. I have a dedicated video here on YouTube about that. It's one of my earlier videos. I'm up against the whiteboard doing that. Put this on here and here and here like so. So if you have a meter with a diode test on it just like this, get this more into focus here, you'll get a beep, or you'll get a solid tone if it's shorted, or you'll get a beep if it's just a standard diode. So since this is an NPN transistor, we want to put the red lead, which is a positive, on the base, and we should get two diodes. So I should get a diode if I touch the collector, and I should also get a diode if I touch the emitter. If I get a solid tone, then it's shorted. Okay, so this should test as two diodes. So I'll hold this onto the base, so I should get a beep, and there's a diode. No problems. And I'll do this here. And a beep. So there's no problems with this transistor. So this is to the emitter right here. See this right here? And this is to the collector. No problems. Again, if something was wrong, I would just get something that sounds like this. All right. So if it's shorted, it would show that. Okay. So now what I'll do is I'll remove that other pass element. And that's off to the side here. All right. So this is a Darlington type transistor. So there's actually two transistors in here in this one case, and there will be some resistors in here as well. How do I know this? Well, I've been working on power supplies for a long time. Okay, so let's see if this meter detects the resistors inside this. Probably won't. Okay, so on. All right, so let's see. This should test as a diode. And it does. And we'll test this. And no problems. And you really can't see that leakage inside here. It's a little high. You have to be really familiar with your meter to recognize something like that. So this is a Darlington transistor, and there's also resistors inside here, and this is not going to show us anything like that. This meter won't. If we were to put this on a curve trace or something like that, we'd definitely see that. So let's see if my little tester detects those things. So let's put this on here. So let's go emitter and collector and base. And yes, it is detecting it. I don't know if you can see that on camera. Two colors are glowing here. The red and the blue are glowing, and this is a little bit of blue in here. So this is more of a pinkish kind of red color. I don't know if I can bump that down. Let's see if I can get that into the focus here. Will it focus on that? You can just see, on my end it's very noticeable, but you can actually see the little red emitter glowing in there. And this one here has the blue and the red glowing as well, but a little bit harder to see. Very little blue glowing. It's up in that little corner there. So this is actually seeing the leakage. I don't know if I can get anything better with that. Let's see. No, it's hard to see on camera because it's so bright, right? Sure, it'd be nice if I could just display that for you. But again, it's just so incredibly... Oh, there you can see them. See a little blue one glowing up in the corner and a little red one glowing in there. So on my end, that's very noticeable, but on camera, it just washes out. So this is actually detecting the leakage, whereas the other meter didn't see it. So there you have it. It went one past. There we go. So there it is. So this is okay, and it's actually seeing the resistors as well. So this is another project that's available on Patreon if you're wanting to build something like this. There's nothing special about this. It's all off-the-shelf parts. You can go to any of your local parts supplier and get the parts for this. And all the plans to make your own circuit board and everything, and the layout is all size and everything up there if you want to put something like this together for yourself. I use the thing all the time. Where I really find this thing useful is, you can see this down here. There's an SOT23 pad, and a lot of the times I'm working with surface mount stuff. I'm just touching the leads together here. I'm working with surface mount stuff, so if I pull a bunch of them off a reel and I have a selection of PNP and NPN and all those on, I can just slide them over and identify them. And if any of them are faulty or if I want to check one, I can just slide it over and test it out on here. It'll also test, you can just plug in the 2SA, 2SB, 2SC, 2SD series or the 2N series in here and test them out and all that kind of stuff. So a neat little tester to have. I use this thing all the time. In fact, I used it earlier today a whole bunch. All right, so far we know that these are okay. What does that tell us so far? Not very good things, because we're getting closer and closer to that obsolete IC, and it's really starting to look like that obsolete IC is bad. Now again, I just turned this thing on, and if the outputs were shorted or something really went bad, these things would just go away. So we're getting close to a part that's, really deep into the power supply that's gone faulty. It's looking, well, at least it's looking like that at this point. Not good. All right, well, I'll just put these things back on top of the power supply and tighten them back down, and we'll start looking for other problems. I'm going to put both of these pass elements back on just the way they are. I'm not going to put any thermal compound on this right now because who knows, I might be taking this thing apart again later on. So in the end, I'm going to clean these off. Maybe I'll even replace these and put new thermal compound on here. And again, I'm going to put a lot of it on there. I'm not going to be skimpy with it. Now, again, you're using common sense, right? You're not going to put a thick layer on it so that it's squeezing down into these holes, and then when you tighten this down, you get this big drippy mess inside. You're using common sense, but you can spread a nice decent amount of this stuff on both sides of this. So again, you don't have to be too sparing. Again, using common sense, right? You're not going to make the thing swim in it or something like that, but you can definitely go easy on it. The nice thing about these sockets here is that, you can just take transistors out and test them. Now, since this is a coarse threaded screw, you have to be kind of careful. If you're going to put these things back in and you find that it gets tight in one spot or something like that, back it out and then try again, because chances are it's not threading in properly. So there we go. And I will put the driver back on just like so. You just wiggle them around like this until they find the pins find the little, I guess you could say, their other mating side. So the little socket, just wiggle it a little bit until it pops into the socket so that it mates properly with the socket. Don't be forcing them down or trying to bend the pins or anything like that, right? So put this on, and like so. Now you don't need to cinch these things down to the point to where you're going to be, snapping the screws off, but just nice and tight. So you just want them nice and tight. And of course, when you put new thermal compound on, when you tighten them down, you're going to get a whole bunch of it squeezing out. And of course, some of it is going to squeeze into those holes where the pins are as well. So what you want to do when you put the stuff on is, when you put the transistor in, usually those pins don't have any thermal compound on them, and they're absolutely fine. If you find that there is, when you smear it on the bottom side of the transistor, and you have the mica spacer on here and things like that, you want to make sure that the pins of the transistor are clean. Try and get as much of that thermal compound off the base and the emitter pins before you slide them into the socket. If not, you're going to have thermal compound in the socket as well. So this is some things to keep in mind, right? Again, a bunch of it's going to squeeze down into that hole where the pin goes. That's fine if a little bit goes down in there, as long as the pins themselves are clean when they go through. That's just a good practice. You don't want that thermal compound all over the emitter and the base leads. Now, I've seen these absolutely smeared with that stuff to the point to where it's dripped down inside the chassis. Of course, that's not using common sense, right? You're not going to be doing that, but it's never really affected the power supplies at all. I've never seen it affect any type of power supply having that thermal compound actually, on the connections here or anything like that. But it's just good practice to keep that about as clean as possible. So at this point, we're getting closer and closer to this thing right here. So let's start going inside here and testing some things. So I'm going to verify that there actually is voltage, and we have voltages on the different parts of the board, and we'll work our way towards this little ceramic IC here. This is what's inside that MC1466L, this little IC right here. So looking at this diagram, pin 14 is the supply for this IC, and pin 7 is the ground. And then we also, in the internal voltage regulator area, we also have, from the cathode side of the Zener diode, a line that runs over to pin 9. So that'll be a bit of a clue in the testing of this without this IC in there. At any rate, we'll worry about that later. So let's test to see if there's any supply voltage from pin 14 to pin 7 here. So I'll just put this in here. Put that onto DC. So I have some sharp probes here. Let's move this out of the way. I can zoom on in a bit so we can see this a little easier. So what I want to do is turn the power on and test from pin 14, which is positive right here, to pin 7, which is negative. So turn this on. I'm going to attempt to do this on camera, so I got to be very careful. So these sharp probes here are insulated right to the tip, so if I slip, I'm not going to short any pins. So let's see here. That should be pin 7 and pin 14. Look at that, 25 volts. Not looking good. So if we also take a look at this, pin 7 here is ground. What drives the pass elements is pin number 5 here. So that's the output to the pass element. So we want to see what's at pin 5. So pin 5 to pin 7. So we'll go back here to pin 7. Again, being very careful. And we'll go to pin 5, which is right here. And there's a little over half a volt on that. And the VR on the face is turned right to the maximum. So it's definitely faulty. And I imagine it's going to be the exact same for the other side. I'll just quickly test the supply voltage here. There it is, 25.4748 volts. There's the leads right on top of the meter. Show you that again. There it is. So these ICs are definitely faulty. That is really unfortunate. The power supply is off, it's unplugged, and the caps are discharged. And at this point, I am just going to set up something. So I found a 10K VR here, and I'll probably use something like this to replace this 10 turn thing over here in the end. At any rate, so what I want to do is I just want to remove the IC and plug this into the socket here. So what I'm going to do is I have my soldering iron warmed up. So I'll get rid of this wire here. And I'll put this, so I just want to put this on the wiper just to limit current. So this is just a 4.7K ohm resistor. Again, this is going to be driving a Darlington transistor, so there's definitely going to be enough current there to turn the whole system on. Let's add a little bit more solder here. Put a bit of solder. Our little friend here, which is 4.7K ohms, he's just going to be here to protect the VR from anything bad happening, just in case something bad does happen. And then I also want to attach a 100 ohm resistor. Let's see, would that be? Yeah, that'd be okay. I'll put it on this lead here. It doesn't really matter which end I put it on. So I can bridge pin 7 to, what was it, pin 9 on there. That's right. So, trying to get this all into the shot here so you can see what I'm doing. So, this on here. I'm just tacking a bunch of leads together is all I'm doing right now. Just so it stays there, just so we can quickly test this thing and see what happens. Okay. So now what I want to do is remove this IC. It's been in there forever. A little bit hard to get out. There it is. Lift them up nice and straight so I don't bend the pins. That came out nice. So put this little fell off to the side here. So we have pin 7 to pin 14. So pin 7 is ground, so I want to use one end of the VR to ground. So we'll go pin 7. And we'll go to pin 9, right? Because we want a 100 ohm resistor to pin 9, just for protection. So the wiper will go to where the output is, so that would drive the pass elements, which was pin 5. Yes, it was pin 5. This would be pin 4, this would be pin 5. And then we would want this one to go to 14. And it goes in there. There it is. Just make sure that's turned towards the ground end. This is the ground end. Okay. So let's see what happens. See if we can get anything to happen on this thing. So prop this up so you can see the meter. So we're going to obviously be on this meter here. And I will put a roll of solder or two under here so we can see this in real time. Okay, so there's, I don't want to wash that out. So there we go. So there is the meter. I'll just move this over here so that we can get a good look on that. So there's the meter. All right, are you ready? Let's see what happens. Here we go. Power on. There it is. So what does that tell us? You can see. See, if I could move very, very fast, I could be the regulator. But that would be extremely fast. I'd have to have reflexes like Bruce Lee in order to do something like that. All right, so what does that tell us? It tells us that both of these are toast. Very interesting. So what I'll do is I will just shut everything off here. You can see obviously there's no regulation. Any type of line voltage movement in that needle is moving. See that? Yeah, that's just bobbing around there. That's my soldering iron at the other end of the bench turning on and off. Right? It's regulating the temperature of the iron. You can even see the movement of the needle just by the iron going on and off. So, As you can see, obviously no regulation whatsoever because the IC's out of there, but that's the way that you can test these things to find that out. So basically just putting a VR in there. All right, I'll shut that off. All right, get this out of the way. And I imagine it's going to be the same for the other side. I could do the same for the other side, but it's just, at this point, it's looking pretty much like it. Well, you know what? Why don't we just check it out at any rate? So what I'll do is I will just take a quick measurement here and see if the other side is discharged. See if this is all discharged, because I don't want to be doing that. Anything here while there's anything happening. All right. Let's go across this cap. No, it is not discharged. That is definitely not discharged. It's going down slow. So I get the cap discharger in here. Zoom on out for a sec. I think it's discharging slowly as I'm actually just moving things around here. So I'll keep an eye on this here. Get rid of any residual charge. Yeah, there you go. Now the pass element, make sure that there's this big can here is discharged. The pass elements are going to be attached to the larger supply, so I'm going to stick the probe into the negative lead because that's going to be part of the supply, and I'll just make sure that there's nothing on these collectors. Nope. So all of the pass elements are going to be okay. They're going to be, or I mean the capacitors that are attached to the pass elements are going to be discharged. See if this one here is discharged. Oh, that one still had a charge on it as well. I could get rid of that. All right, safely discharged. Get that out of the way. Move that out of here. Stick my hands in here and get this thing out. Okay, another one out. Let's get this guy out of the way. Unplug our test jig. So we go from pin 7 to 9. This one should go to pin 5. All right, let's check out this side. I have a feeling it's going to be absolutely the same. So this time, oops, let's put this here like so that doesn't slip. Again, keep an eye on this. Turn that right down. Turn that on. There it is. So yes, both of those ICs are toast. Since both of these ICs are faulty and they're getting very hard to come by nowadays, and these capacitors are going to need changing, this one here most likely too, I'm thinking that I want to make something that I can service down the road because I really like this power supply. So you know what? I think I might actually just design a new board and replace this. So what I'm going to do is I'm going to take off all of these connectors. They should just pop off like so. So I'll remove all of these wires and connectors and take this board out, and we'll take a closer look at this board. And I'll talk a little bit about my thought process as I'm going to go about redesigning this and putting a completely different board in here with a different type of regulator IC and everything. Here's the regulator board out of the power supply, and it really came out quite easy. So this is just basically pushed down onto some plastic standoffs. So you just kind of go click, click, and it just pops off like that. And then you just pull little wires off of these connections here, and the whole board comes right out. So it's very easily serviceable. So way back in the day when the power supply was closer to being new than it is now, you could have probably called up Anatech if you had any problems, and they just ship you out a new board, or maybe just even an IC or whatever you need, and you could have your power supply up and running in no time. Now, since the components on this board are outdated and hard to find, what I'm going to do is just redesign another board and fit it in there with components that I can find that are readily available. So I want to make sure that my board fits into the exact same spot that this one came out of. So I need to make sure that the measurements between the holes are exact, and I also want to make sure that the board is exactly the same size. I want to reuse these connections here, all of these connections here, so I got to remove these from this board. And I'm going to install these into my board, and I want all the remaining wires that are in the power supply to attach to the same area that they attach to on this board. So basically my board is just a direct replacement. It plugs right in, maybe with only some minor modifications, something like that. Now usually these capacitors here, made in Canada. Usually these capacitors are very good, even to this day. So what I'm going to do is do a thorough test on this capacitor, and if it is still good, I'm going to reuse this in my design. It'd be kind of neat to have that in there because it'll look something like the original board. But again, it'll be quite different with modern components because it'll be completely different design. So I have a lot of measuring to do. I'll get started on that, and when I have some results, I will be back. All right, I've taken a whole bunch of measurements here, and I've also mapped out where all the pins go on the board so I can reconnect the same wires and of course design my new supply to fit in place of this existing board. Tested the capacitor tests extremely well, so I will reuse that capacitor. So you can see here we have the power transformer down here, and it attaches to this area of the board right here. So the two red leads, which is one winding out of the power transformer, runs just over to the MC1466L. All right, and then we have the green, a green, yellow, and a green. So the ends of this winding here attach right to here, and what they've done in this is they're running a full wave bridge rectifier here, and then the center tap is rectified as well. The center tap, of course, is half of what the end-to-end voltage is. So if we have, 44 volts, we're going to have 22 here, right? So we have 22 volts at this point right here running to the collector of the 2N3055, right? So this is the one that connects to the post on the front here. This is a 25 volt regulated power supply. Under load, that'll drop to about 20 or some odd volts. So the MJ1000, which is just behind it, which is driving this, is doing some of the work as well because there's 40 some odd volts on the collector of this transistor. Very interesting design. So of course, when I design my supply, I have to design this, whole idea into that as well. So this runs off to the current limit over here. And then of course we have the black and the white. So the black is the negative lead and the white is the positive that runs out to the current meter and then out to the post. Then of course the voltmeter is just across those posts. And this here is what sets the voltage. Voltage set over here. Pretty straightforward. So I'm on my way to starting the design here. So of course I've measured up everything so the new board will just pop right down in. And the capacitor is, the way that they've mounted this is kind of on a bit of an angle, as you can see that. So I'll just have this straight like this on my design. A little bit easier, don't need to have it mounted like that. So lots of things to think about. So away I go. I'll start designing a board and I will be back soon with some ICs. I'm going to design this board with some ICs that are readily available, or at least something that I have right now. I ended up using a few components off the old board, so I used that main filter capacitor and two resistors, aside from the little pins or the connections that I've removed from the board. Now, believe it or not, removing those connections from this board was a real big pain, one of the biggest pains of actually doing this entire project. What they had done is they pushed the pin through on the top side, and on the bottom they open it up, so they kind of crimp it, or I guess you could say part the metal on the bottom, and they've soldered it after that. So I'd have to desolder it, really, really well. And then where they've crimped it, I had to pinch it all back together again. So basically fold it together and then pull the pin out of the top side of the board. So a lot of work, because that's a lot of pins. And then after that, I had to clean the pins up and then put them into the new circuit board, which is right here. So this is the newly designed board that will be on one side. There'll be two of these inside that unit. So at this point, I just have this one done. So this is pretty much the same thing. It does pretty much the same as this board right here. The difference is instead of having one IC like this one has two ICs. And the ICs that I chose for this are the UA723. So I'll zoom on into this here. You can take a closer look. So these are the two resistors that I've taken off the other board. And as you can see, on this board, I soldered the pins on the top side as well as the bottom side. So this is very sturdy now, whereas on the old board, it was just the bottom side that they were soldered in, right? So that is all done. So this here is the current adjustment. So I can set the maximum amount of current right here. And on the bottom side is pretty much the business end of things here. So there's two UA723 ICs here, and these are readily available, unlike the LM723 now. So these are still available, and I have quite a few of them, so if anything ever does go wrong with this, I can very easily just replace those ICs. So the reason that there's two is one is a negative 5 volt supply here. So you can look at this little area right here, like the mini version of this entire power supply. So this is the pass transistor right here, and this UA723 controls this. This adjusts the negative 5 volts. The reason I need negative 5 volts is because this IC here is doing what the original IC on this board did right here. Now the UA723 will not go down right to 0 volts. So in order to make this go right down to 0 volts or very close to, I need to create a stable negative 5 volt supply for this so that I can bring it down that low. So this is the negative 5 volt supply set, and this is the 0 set for this side. And I'll have to adjust all of that once that's inside that power supply. So the way I've designed this is, you know how there's a little border cutout on the bottom. All the adjustments are very easy to get at on the bottom. I don't really need to worry about that. So the diodes that you see on here, these large diodes on the top, are surface mount diodes right here. So these are 100 volt 6 amp surface mount diodes right here. See, what else can I tell you? There's another one here. That's from that center tap. There's a bunch of shot keys to stop things from going negative. So there's a bunch of hitches whenever you design something new like this. So when I say going negative, what happens is because this has two separate regulators in here, this negative 5 volt supply has to stay at negative 5 volts while the main power supply capacitor discharges, and that is discharged by this resistor right here. So as soon as the power is shut off, this resistor right here is discharging this capacitor immediately. The reason that these two capacitors are so large over here, so you can see 3300 microfarad at 35 volts, is to keep this supply up, the negative 5 volt supply, while the other one discharges. If not, what'll end up happening with the supply is if this goes away first or goes away quicker, what ends up happening is the power supply will actually go down a bit, and then it'll raise in voltage again, and then it'll slowly come back down. So everything needs to be kept stable. So now this also, there's another capacitor here, which also is with a Zener diode. You can see this little Zener diode here. So this is regulated here as well. And then that runs into this IC. So that also has to keep everything nice and stable. So there's a lot of things going on here. So quite a bit of planning and design work. So this little diode here there's a little diode under here with a heatsink on top of it, and I designed an area, a whole bunch of, I guess you could say a lot of copper area here for this to act as a heatsink. So this diode is in series with these current shunt resistors, really is what these things are. So, or current sense resistors, I should call them. So what ends up happening here is, because the way the IC works in this circuit, there isn't enough drop across this to properly operate the current sense section in this, right? There's a current sense transistor inside the UA723, and of course the transistor needs 0.6 of a volt to turn it on, right? So what happens is, since this diode here is in series with these resistors here, it allows me to establish that 0.6 of a volt plus, and I can adjust it with this here so that I can get that variable current control on the front of the unit. So that's how that all has happened on here. What else can I tell you about this thing? It's, pretty much what's going on here in a nutshell. I could, really get into the specifics of this, but I'd be talking for a long time. So now to put this thing inside the power supply and change that variable resistor on the one side, that 10-turn variable resistor drives me nuts. So anyways, I'll get rid of that thing, put a single, 1 turn or whatever, it would be just about 1 turn, variable resistor in there, and put this in, and we'll try it out, see how well the thing works. I have the new regulator board installed, and it fit in just perfectly. So lots of time and measurement paid off. All the wires are all in place. Everything is ready to test. I also changed that variable resistor. So it's pretty much ready to go. Now, whenever I design anything, I design around center values. So what I mean is, when I put the VRs in, you can see this is pretty much in the center. All the VRs should be sitting very close to their center position. That's the way they come out of the package, right? So they should be sitting very close to their center positions, and I should have very close to -5 volts. I should also have very close to 0 volts on the meter here, and they should be sitting somewhere around 2 amps. It should be current limiting somewhere around that. So it should come in close. So what I'm going to do is I'm just going to prop this thing up, and I'll secure this so that it doesn't move around. I don't want to short anything out and damage this board and then have to go about fixing this. So I'll just make sure everything is, nice and sturdy. I'll prop this thing up, and we'll take a look at it. I'll turn it on, and we'll check out its functions. The first thing I want to do is check the -5 volt supply and see how close that is. So I'll turn this on. I have the meter attached to the ground post on the front just with an alligator clip, and I want to see if this is at 5 volts, and if not, I'm going to adjust this. Again, so -5 volts. So I'll turn this on, and I'll come in here with my sharp probe, touch the test point. That's pretty close, 5.02. So I think this end here has got the sharper of the two. What's this one here? I'll just move this in here, like so. All right, 5 volts right there. So that's set. Now the next thing I want to do is check the 0. So I'll put this in here. I'm at 0.74. Oh, that's so close. I don't even think I need to worry about that. So if I adjust the 0, again, one of the ends on this thing is sharper, so I like using that end. And I'm going negative now, so you can see I can adjust the 0 way up, right? 0.3 of a volt, 0.2, 0.1. And that's 0 volts right there. So that's set. So now that that is all set, I'll move this. I'll stand this up, and we can take a look at the meter on the face, and we'll load it, and we'll see how well this deals with a load. All right, let's try out the power supply. So I'll turn this on. I must not have this sitting right at 0. I must have bumped that. There we go. So 0. Now keep in mind that these meters are not going to be completely accurate because the power supply is sitting on an angle. It's propped up by 3 rolls of solder here, so we can see this in the camera. In order for the meters to read completely accurate, this needs to be sitting on a flat surface. It's very common for meters like this to be like that. So I know before the power supply failed, these meters were very accurate, so I'm pretty confident in that. So I'll turn this up. Look at how smooth that is. Very nice. Very happy with that. Much nicer than that 10 turn. It's very easy to dial, and look at that. If I want 15 volts, there's 15 volts. If I want 10, there's 10 right there. If I want 5, there's 5, so on. So it's very nice. So now what I need to do is I need to set up the current limit. So the meter, it ends at 2 amps, but I really want this to supply about 2.2 amps because this is a really soft current limiting action in this thing. So what I'm going to do here is turn this right down. I have a 5 ohm resistor here, okay? Big 5 ohm resistor. So I'll just use that as the load. It's very accurate. It is right at 5 ohms. And what I'm going to do is turn this up to 5 volts. So 5 volts into 5 ohms should give us 1 amp. I'll turn this up. And that's really close to 1 amp right there. Pretty much sitting right on the 5. And as you can see, it's really close. Again, a little bit of inaccuracy because this is on an angle. So not too bad. So if I turn this up to 10 volts into 5 ohms, we should have 2 amps. And it's very close. So now, if I turn this up, you can see this is going way over. So that should be current limiting out at about 2.2 amps. All right. And I'm sure this will go much, much higher. So what I'm going to do is I'll very carefully put my screwdriver into this VR here. And I want to turn this up. And I want to bring this back down to about, turn that way up. I'll bring that to about 2.2 amps. So this is right at the end. So if I was to remove this cable, it'd go right up to about 27 volts. So about 2.2. Boy, that's right there. Close enough. All right, so I can turn that down. So I go to, yeah, that's looking really good. Lots of cables and loss and stuff like that happening here, so it's close enough. That's very, very close. Now, what I want to do is I want to see if this is going to current limit correctly. So, say I've got 1 amp happening, okay? I want to turn this down. I can turn that down to, say, 0.5 of an amp, or even lower. You can see that, so I'll bring this right up to about 2 amps. You can see that I can current limit this out. So it'll top out at about 2.2, right? Bring it down to supply 1.5 amps right there. Or 1 amp, or 0.5 of an amp, right down. So that's working very well. I'm very happy with the results. Oh yeah, I should demonstrate the regulation, how well this regulates. So I'll turn this up to about 5 volts, somewhere in there, just like this. Now I'll add 1 amp worth of load here. And as you can see, the voltmeter doesn't even move. I'll bring this up to about 8 volts. Now, this will start to current limit out at about 10 volts. So it's that soft current limiting action, so it should hold pretty solid right at about 8. As you can see, just still rock solid. And when I bring this right up to 10 volts, so I'm going to be right at about 2 amps, and it's going to start to soft current limit, you'll see just a little bit of movement in the needle. In fact, I'll bring it just a touch above. So here we go. There you go. Just a little bit of movement. Hardly anything at all. So it's working very well. Now, of course, I could make this completely solid by upping that VR inside again, but I want that soft limit in there. Now the fun begins. I have to build another one all over again for the other side. That's a lot of time into this thing. But at any rate, I hope you enjoyed, and I'm going to talk a lot more about power supplies here very soon. I have a bunch of schematics and stuff ready. We're actually dealing with some power supplies and high voltage supplies and things like that on Patreon right now. So I'll talk a little bit more about this up there very, very shortly, probably within the next day or two. I'll have a video up about this, of course, from the date that this video is produced. And, I'll have another video on this, and maybe I'll even expose the schematic and everything for this and talk a little bit about this there as well. So I hope you enjoyed the video, and that's the power supply. Project done and very successful. I'm very happy with that. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So there'll be a lot of troubleshooting, repairs, diagnosis, and lots of restorations coming on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you want to be notified as soon as I post a new video, don't forget to tap that bell symbol. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal inventions and designs, you're going to definitely want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time. Take care. Bye for now.